Okay, small picture of the situation in problem 2. Projectiles fired from a 5-meter height at 10 meters per second, lands 15 meters away. What's the angle of elevation? Now, just to frame the problem, or to understand a little bit, we know that a projectile will fall actually 4.9 meters in 1 second. So this is going to take about 1 second to fall. If this was fired at a horizontal at 10 meters per second, then it would only travel 10 meters in this direction. So hopefully there's some angle at which we can fire it so that we get extra time in the air without too much compromising our horizontal velocity and achieve a distance of a horizontal range of 15 meters. It's not assured that we can do this, and if we can't, we're going to end up with a negative under a discriminant somewhere, but it's a good way to start and to think about this problem and what could happen. Now, having done that, we're going to set this up purely in terms of vectors. We know the acceleration is just that of gravity, negative 9.8 meters per second times j. The initial velocity is what? Well, it's v naught cosine theta times I plus v naught sine theta times j, where theta is your angle of inclination. And we could add that to our picture here. So there's our theta. Now v naught we know to be the magnitude of v naught to be 10 meters per second, so we could easily replace the v naughts with 10 meters per second and come up with various solutions. And I've kind of substituted numbers in a lot of places, but I've left the v naught as a v naught. But that's a given quantity, and at any stage we could substitute 10 meters per second. Okay, so we also know that if T naught is the initial instant and TF the final instant, and I didn't write that out just to save board space, and if we assume that T naught, the initial instant, is 0, so the time runs from 0 here to TF here, then S of 0, of course, is just 5 meters times j relative to an origin here. Now, we could have done all this relative to this point, and then S of 0 would be 0. In either case, S of TF, well, S of TF, if the origin is here, is just 15 meters to the right of the origin. That corresponds to the vector 15 meters times I. Now, had we started up here, then the S of TF would have had to been 15 meters times I minus 5 meters times j. So we would have gotten a 0, would have had a 0 here, but we would have had 2 components up here. That's kind of a trade-off. It could be set up either way. Chosen to set it up this way. And it wouldn't be a bad exercise to set it up the other way to see how everything relates. Okay, well, that's the information we're given. Of course, as I say, I didn't substitute for v naught, but we can keep in mind that that's given. Okay, so we integrate our acceleration function to get our velocity function. Okay, that's easily enough done. Our acceleration function is very simple. Yeah, I left off a t right here. So simple as it is, I kind of messed it up. I've been doing way too much of that stuff, as everybody knows. Okay. So we integrate this, just a constant times j. Well, the result is going to be that constant times t times j. So negative 9.8 meters per second squared times t times j plus an integration constant c1. Now, we're used to integration constants being just plain old numbers, but now we're integrating a vector function. Our integration constant is going to be a vector function. It's going to have an arbitrary I component and an arbitrary j component. Why is that? Well, if this is a constant vector with a constant I and a constant j component, then if we take the derivative of it, we get 0. So that the derivative of this for any constant vector is going to be negative 9.8 meters per second squared times j. Okay? Well, we proceed, and I'm going to let the C1 be a C1xi plus a C1yj. just to be sure that we understand that this constant vector has an I and a j component. And of course the j component also, there's also a negative 9.8 meter per second squared times t multiplied by j. I put parentheses here so that t doesn't look like part of the units, and the same thing here. Now, we also know, since v of 0 equals what it equals, v naught cosine ti plus v naught sine tj. Now, I didn't do this step explicitly, but if this is our v of t, then using our initial condition gives us v of t equals this. Why? Because v of 0, which needs to be this, is just equal, since this has a t in it, t is going to be 0, that's going to be 0, it's going to be equal to v naught cosine theta I plus v naught sine theta j. Well, it's going to be equal to c1x I plus c1y j. That is going to have to equal v naught cosine theta I plus v naught sine theta j. And we immediately conclude that c1x has to be v naught cosine theta, I component equals I component, and j component equals j component. C1y is v naught sine theta, so times j. So here's our function, and that's very straightforward. I think everybody is okay with that, but be sure to let me know if you aren't. Now, what do we do next? Well, we now integrate v of t. We get s of t equals what? Well, it's going to be v naught cosine theta t I, because the only I component is just this one, or the only term here that's a multiple of the I vector is this one. We integrate it, we're going to get a t. So we got v naught cosine theta times t, and then we integrate our t here, we get a t squared over 2. The coefficient negative 9.8 becomes half that, negative 4.9. And integrating v naught sine t with respect to t, our antiderivative is going to be v naught sine theta times t. Now there are integration constants both here and here, but we just combine those into a c2 vector, so our integration constant is going to be our c2 vector. Now I just realized I got this bright shirt on, so this board is fading in and out as I move closer and further. I'll change that in a couple of minutes here. Okay, so now, I neglected to evaluate my C2 here. I've done that up here. S of 0 equals C2, and S of 0 equals 5 meters times J. So our C2 vector is just 5 meters times J, so that we just add that in to the J components. And I have something else here, another error, because I'm clear to be incapable of writing things down correctly. So let me fix it. Okay, I had the j inside the parentheses on one of the terms rather than outside the parentheses, so it would apply to both the j terms. So I fixed that. Messed this up a little bit, but you can still read it. Okay. Okay, then, well, C2 is 5 meters times j. So I just incorporate that in the expression for the j component. And I have this, and also this is S of TF, so I substituted TF for T. So S of TF is this. S of T is what we have here. Okay, I've put the 5 meters in here within the J component. That's the only change from here to here. And this then implies that S of TF is what I've got written here. And of course, looks like I've rewritten it. I had a reason to rewrite it before because I hadn't done this, but it's just written twice. But then that's got to be equal to 15 meters times I, because that is what S of TF is. Excuse me, according to our picture and our reasoning for setting up the problem. So we got S of TF equals this, equals 15 meters times I. And now, yeah, I'm okay. Now, the I component here has to equal the I component here. We get this equation. The J component equals the j component here. Well, the j component over here is 0, so the j component is just going to be, well, this expression is going to equal 0. So that's our second equation. Now, the equation is a little bit daunting if you haven't solved equations of this nature, but there are many ways to go about it. We eliminate one variable. We could solve the second equation for TF. Of course, it's quadratic, so we get two possible solutions. Perhaps we could dismiss one of them, and perhaps not. I see something else I want to change in the notation. Order of operations dictate that this is the way you interpret this expression, but without the parentheses, it can look a little bit confusing, and there's no point in confusing ourselves. Okay, so strategy for solving the problem. We eliminate one variable. We could eliminate TF, but we have two possible solutions, and we might or might not be able to eliminate or choose either the plus or the minus until we've been through the whole solution. That would mean we'd have to substitute two possible values of TF up here in order to solve for theta. Easier, we could solve this one for theta. We could solve it. Theta is the arc cosine of 15 meters over V naught T. TF. That's a little cumbersome, although it would work because the only theta we have here is in the sine, so we could take the sine of that arc cosine. That would be perfectly acceptable. It's going to be completely equivalent to what I've chosen to do, which is to say, okay, well, we can solve this. We got a V naught sine theta here, and we can solve this for V naught cosine theta. But just V naught cosine theta is 15 meters over TF, which means, and you can work out why, and you can work it out a different way if you like, but V naught sine theta is then going to be the square root of V naught squared minus the quantity 15 meters over TF quantity squared. Now, I hope I did that right, and if I didn't, maybe you'll check up on me and figure it out. There are other ways to solve the equation. You should be able to do it. This is one way that I'm just illustrating. Okay. Now, if we substitute this for V naught sine theta, because I can substitute this for the whole V naught sine theta, I get this. The only difference between this equation and this equation is that V naught sine theta has been replaced by this expression. Okay? Now, at this stage, we can use the quadratic formula. It's going to be kind of messy because you're going to have your negative b term, and the at squared plus bt plus b is going to be a square root here. So you're going to have a square root there, and then you're going to have plus or minus another square root. Now, inside that square root, you will have the square of this, and then minus this coefficient times 4, and that'll work out. But you'll have two square roots to deal with, and maybe or maybe not you can find a good way to simplify that. In any case, once you get this, you can solve for TF and then substitute that back in and solve for theta. Now, there are other and in some cases easier ways or more direct ways to solve this, but that is one way.